Here we have 9.3a, and we're going to be talking about optimization, specifically the second derivative test. A company has modeled their profit with the following curve. So below we have the graph where the quantity is on the x-axis and the profit is on the y-axis. In order to maximize their profit, how many items should they produce? Well, by inspection, we could see that x equals 7 yields the maximum profit. And we could call this the maximum. So if we wanted to, we could say that 7 items would yield the max profit for this company. But we can remember that through calculus, we can find this maximum point when it corresponds to the derivative being 0. So if we were to draw a tangent line, or the derivative at this point, we could say that f prime at 7 equals 0. This sort of question is called an optimization problem. Optimization problems require the calculation of a maximum or minimum amount, and in many cases can only be determined using calculus. Over the next few lessons, we will learn strategies to find these optimal values. So the second derivative test is a tool that allows us to quickly determine if a critical point is a relative maximum or a relative minimum. It combines information that we know about the first and second derivative. So for the first function, we have a function that concaves down, and for the second function, we have a function that concaves up. For the first one, by inspection, we can see that at some point x equals c, there is a relative maximum. In general, we can find relative maximums only on function intervals that are concave down. So in specific, we require a critical point, so the first derivative at that point c has to equal 0, and that it is concave down, or that the second derivative at x equals c is negative. Likewise, for the function on the right, it's concave up, so at x equals c, there's a relative minimum. So relative minimums only occur on function intervals that are concave up. Specifically that the critical point has f prime at x equals c equals 0, and that it is concave up, so the second derivative at x equals c is positive. In general, this can be summarized through the second derivative test. If the first derivative at x equals c is equal to 0, and the second derivative at x equals c is positive, then we can say that the function f has a relative minimum at x equals c. Likewise, if the first derivative at c is 0 and the second derivative at c is less than 0, so it's negative, then the function f has a relative maximum at x equals c. But we also should consider when f double prime, or the second derivative at c, is 0. Then the second derivative test fails, and we must use a sign diagram to check if x equals c is a relative maximum or minimum. I'd just like to make a note, you could happily live your life without ever using the second derivative test. For example, when we teach optimization in a non-IB calculus course, we usually don't include this lesson. To find the relative max or min, you can just use the first derivative test and a sign diagram. However, periodically, an IB question will give you information that makes it more timely to use the second derivative test. And in rare cases, you may see a question that specifically asks you to use the second derivative test. For example, use the second derivative test to justify that b is a maximum. So here's an example. For the function f at x equals x cubed minus 3x squared minus 9x plus 5, find the relative maximum and relative minimum points. So the first thing we're going to do is find the first derivative. So we'll see that f prime of x is equal to 3x squared minus 6x minus 9. Next, you want to find the critical points. So you need to set f prime of x equal to 0. So here we have 0 is equal to 3x squared minus 6x minus 9. We see that there's a common factor of 3. So we can factor that out of the whole function, which reads 0 is equal to 3, and in brackets, x squared minus 2x minus 3. This can easily be factored into x minus 3 and x plus 1. So we have that a potential critical point is x equals 3, and the other critical point is x equals negative 1. As these are possible maximum and minimum points, we apply the second derivative test. So we get the second derivative, f double prime of x is equal to 6x minus 6. And we'll consider each critical point separately. So let's start off with at x equals 3. So at x equals 3, we'll substitute in x equals 3 into the second derivative. So we'll read it as 6 times 3 minus 6. This gives us 18 minus 6, and finally 12, which is a positive number. So therefore, we can conclude that there is a relative minimum at x equals 3 because x equals 3 had a critical point, and the second derivative was positive at this point. Now let's consider x equals negative 1. At x equals negative 1, we substitute x equals negative 1 into the second derivative, which gives us 6 times negative 1 minus 6. This gives us negative 6 minus 6, which gives us negative 12. This is a negative number. Therefore, we can conclude that there is a relative maximum at x equals negative 1 because x equals negative 1 is a critical point, and that the second derivative was negative at x equals negative 1.
And here we have an example where the second derivative test is going to fail. So we're asked to find the relative extrema of y equals 4x to the 5 minus 6x to the 4. So the first thing we're going to do is find the first derivative, which is y prime is equal to 20x to the 4 minus 24x cubed. Then we're going to check for the critical points. So we set y prime equal to 0. This gives us 0 is equal to 20x to the 4 minus 24x cubed. We can factor out a common factor of 4x cubed, which gives us 5x minus 6 in brackets. And this will give us x equals 0, as well as x equals 6 over 5. These are possible maximum and minimum points, so we apply the second derivative test. First, we find the second derivative. So we'll take the derivative of the first derivative to give us y double prime equals 80x cubed minus 72x squared. So let's check x equals 0. At x equals 0, we'll get that y double prime equals 80 times 0 cubed minus 72 0 squared. This equals 0. So the second derivative test fails. So we'll follow the last point of the second derivative test where it says if it fails, we must use the first derivative test and check using a sign diagram. So we get our line that shows the sign of y prime, and we put our two possible points, x equals 0 and x equals 6 over 5. Then we'll consider all of the regions before, in the middle, and after. So we'll consider all of the negative values, so x less than 0. We'll check the values between 0 and 6 over 5, as well as the values greater than 6 over 5. Then we put in all of our factors. So we'll have 4x cubed and 5x minus 6. Notice that we could use the value above, whereas 20x to the 4 minus x cubed. But it can be difficult working with these large values, so it might be easier to separate it using the factored form. So 4 is always positive regardless of what x value we have. So we'll put a plus in all of the values. For x cubed, if we have a negative value, like negative 1, if we put it into x cubed, we'll still get a negative number. For 0 less than x less than 6 over 5, we can consider a number like 1. If we put positive 1 into x cubed, we'll get a positive number. And lastly, if we get x greater than 6 over 5, we can consider a number like 2. Positive 2 cubed will give us positive 8, so we'll get a positive number. Now for 5x minus 6. If we consider a number like x equals negative 1, we'll get negative 5 minus 6 will equal negative 11. That's a negative number. For the region between 0 and 6 over 5, let's take the value 1. So 5 minus 6 will equal negative 1. So again, another negative number. And for x greater than 6 over 5, we can take the number 2, and that'll be 10 minus 6, and that'll be a positive number. Then we look down the columns, and we see that a positive and 2 negatives make a positive, 2 positives and a negative make a negative, and 3 positives make a positive. So we put these corresponding signs into our line above. So before 0, it'll be positive. Between 0 and 6 over 5, it's negative. And from 6 over 5 onwards, it's going to be positive. So we'll now consider the signs. Before 0, it goes from positive to negative. So we can say that there is a relative maximum at x equals 0. For 6 over 5, from left to right, we're going from a negative to a positive. So we're decreasing then increasing. So this is a relative minimum. So as we can see, although the second derivative test failed and we weren't able to use it, we can still use the sign diagram and the first derivative test in order to find any relative maximum or minimum. Therefore, we can say that there's a relative max at x equals 0 and a relative min at x equals 6 over 5. And here's your homework. Do page 242, numbers 1 to 6.